Okay, then welcome everyone to my talk about the scene representation and visual search DFT model. I have to get rid of okay. Sorry, there was a Zoom overlay here. So, as you have seen in John's great talk, most DFT models of higher cognition share two core subnetworks that are crucial for the object-oriented interaction with the environment. The first one is the visual search subnetwork that consists of a bottom-up feed-forward feature extraction path and a top-down guidance path. And the second one is the scene memory subnetwork that we also sometimes call scene representation, because I prefer the term scene memory when it's in short-time memory and scene representation when it's in long-time memory. And this one autonomously builds the working memory feature representation of previously attended objects. And here I'm going to present a neurodynamic process model that builds on these two core subnetworks to account for the difference between featured and conjunctive search. And in this context, I will also address the question of whether both the overall speed and efficiency of conjunctive visual search can be improved by scene memory. And I will also explain how we extended this model to understand the interplay between bottom-up processing and top-down guidance in visual search, an issue in need of theoretical resolution. First of all, a short background. So anyone who's familiar with N. Treisman's feature integration theory knows that N. Treisman, in a classical view of N. Treisman, visual search was either parallel or serial. So feature search was parallel and conjunctive search was serial. Jerry Wolf, on the other hand, described the efficiency of visual search as forming a continuum, so going from efficient until very inefficient. And he defined the slope of reaction time against set size function as the measure of efficiency. By this measure, single feature search, so where only one feature is queued, is efficient as the reaction times are independent of set size. So we have this flat slope. And one also can say that the target pops out. And in the conjunctive case, the reaction times are proportional to the number of distractor items. So we have a steep slope, and in this case, well, it's inefficient. Okay, now we come to the role of memory in visual search. This is quite a controversial topic, and it has been intensely studied in a variety of experimental paradigms with a plethora of different findings. And one of the prominent paradigms is the preview paradigm. And here we have an example from an Hollywood paper where we can see that people are presented a scene, then are queued for a probe after some time, and then they have to look for it. And with the preview, they will find the item faster than without preview. This is true for naturalistic settings. Okay, sorry, I think that recording and sharing at the same time, it's very making my PC very slow. I've pressed and nothing happens. Okay. Hillstrom and colleagues extended this work by showing that information on the list of the scene alone can already improve search efficiency. But also in this experiment, the effects were only found for naturalistic scenes and not for classical random ordered search arrays. One finding that is common along all these kind of experiments in the preview paradigm is that the mean reaction times are reduced, but not the efficiency. So the slope doesn't change, but the intercept of the function. Becker and Peschler, who also tried to find this effect for many years, argued that at least this difference in the intercept was a strong evidence for guidance of attention by visual working memory, but they also didn't find any change in the efficiency. Okay, so we created a new scenario that we also tested experimentally in our lab, and the scenario is the following one. So it's the same scenario for the model and the experiments. There's a preview of a scene, and there is a marked place where after some time the target appears, and this target is the cue for the visual search. So we see that here's the target and here's the cue, and then people and the model had to respond by indicating the location of a matching visual object, meaning that this was a location task. That's also very important. We choose this preview paradigm as the key behavioral task to address with the DFT model, and specifically address the question why preview benefits that was observed for natural scenes did not generalize to randomly arranged search arrays. So the experiment had, the first experiment we did had 3 conditions. The first condition was the baseline condition, so it was a simple feature search. The second condition was the preview condition. So we had a conjunctive search with a preview of the scene for 800 milliseconds. And the third condition was the classical conjunctive search without preview. So we had this two, as a baseline, we had the single feature and the conjunctive search, and the more interesting condition was this preview condition. Importantly, in this condition there was no break between, so the scene was always present. We also did an experiment with a white break in the middle, but that's not so important currently. What we can see here is that the slope for the single feature condition 1 was near to 0, so as expected. It was a very efficient search. The condition 3, so the conjunctive case, was as expected inefficient. But the condition 2, as you can see here, the difference in slope is around 5, and this was the first experimental evidence for really a difference in the efficiency. If you're interested, you can look up at the Grieben et al. Paper in Attention in APP 2020 last year, and there we have also a mathematical explanation why this difference is really the correct difference. It may not be obvious, because you could say, okay, there's a very small difference in the efficiency, but this is really the correct difference, and this results from the capacity limitation of visual working memory. Okay, so now we will go to the model. It's important to know that since there was no experimental evidence for this interference between scene memory and visual search, so you wouldn't be able to really model it. So it was important to find these experimental results and to understand them, to be able to now model them. And so we created a model that was able to fulfill the task, and for fulfilling this task we need to model 3 fundamental processes of visual cognition. One was explore a visual array, meaning that was the preview condition. So in the absence of a task, it would explore the scene by creating sequence of attentional selection decisions that are only biased by bottom-up input, and then committing the perceived features value to scene memory. The second one was shifting the attention to locations at which visual transients are detected, so meaning that if the target cue appears, that you can notice this change in the scene, attend the location of the cue, and then commit this feature information to the working memory of the feature cue. And finally, search for location in the visual array at which this cued feature match the conjunction that was previously presented. Okay. This is a very schematic overview of the model. Boxes presenting subnetworks of neurodynamic fields, and the arrows the coupling between them. And now I will guide you through 3 subsystems of the model that are important for all of the tasks, and then I will explain how the tasks evolve from the underlying dynamics. So the first subsystem is the feed-forward feature and salience maps. Since visual cognition builds on visual input from which features are extracted, visual input may take the form of a video stream, like we did in a previous Coxeye paper. But in the APP paper, we used sequence of synthetic images, since we used the same images that we presented to the participants in our experiment. And yeah. Okay. And 3 simple features are used in the model: color, orientation, and size. And color is only simply extracting hue space from RGB values. Orientation is the saturation that is passed through a threshold function and 4 elongated center surround filters. And size is using a hierarchical pyramid of center surround filters with increasing size and a one-way inhibition along the scale dimension. And then the normalized output of the feature extraction pathway provides the input into 3 space feature fields, with each combined 2 dimensions of visual space, so this x and y, and 1 dimension of one feature dimension, in this case color, orientation, and size. And each of these maps projects into the scene space a salience field. This projection is purely spatial. Okay. Sorry. Okay, the second subsystem is the attentional selection, since visual cognition always entails attentional selection decisions. And this is the subsystem of the neurodynamic architecture that generates such selection decisions. Central is the scene space selection field that represents the current attended location, the current spatial attended location, of course. And this field is in the dynamic regime of selection, meaning that it can only support one single superthreshold peak at any point in time. It receives input from the salience field, from the feed-forward path, and it will select the most salient location in this input, but it also receives all biased input from 3 additional sources. First, it's biased away from previously attended location by the inhibition of return memory trace. Second, it's biased away from locations that receive inhibitory input from the spatial working memory field, and that was filled by missing a slide here. So the input from this field was during the exploration field, that any object, that feature location that is committed to the scene memory is also committed to the spatial working memory field. So it's contained the locations that are stored in visual working memory. Sorry, it's hanging again. Wow. Okay. The sustained peaks in this memory field, are however destabilized when movement is detected in the scene. So this happens through a 2-layer offset detector. So if activation moves or vanishes in this field, the offset detector will create a peak and destabilize the information in this peak, so the peak will decay. This was important because in the second experiment, as I mentioned before, we had a pause in between with a blank screen, and this pause in between made that the efficiency effect were lost in the experiment, and the explanation for this loss of information was due to this offset detector. that's also the reason why we have the spatial working memory field. We could also argue that you could get information about the location from visual working memory directly, but in the second experiment we showed that these are different paths. So the location, spatial inhibition, and the scene memory have different effects on the experiment. Importantly, the number of peaks that can be simultaneously sustained in the spatial working memory field is limited by accumulating inhibition. This is important because, as everyone knows, capacity of working memory is highly limited, normally at around 4 items. And so by tuning the correct parameters, you can create a balance between neural inhibition and excitation, and so you can have influence how many peaks can be created in this field. And this constraint was important for fitting the experimental results. Third bias is that attention is attracted to locations at which rapid changes of spatial salience occur. So if here a new input is created in this field, so a new peak emerges, this transient activation change will create a peak in the onset detector, and then this one will then activate the retain node, and that's the second task, and we will see how this will work. So the attention is then biased to this new location. And this is a very strong bias, meaning that that's also in reality in experimental data we know that transients have a very, very strong influence on attention, and that this is such a strong influence that you can't even prevent from looking to the transient. Spatial attention represented by a single self-stabilized peak is a critical role in feature binding, as Professor Schöner has shown in his previous talks. We use this single peak in the spatial attention field to have a neural implementation of N-Treatment binding through space. The third subsystem is the feature matching subsystem, and this compares features in parallel across all feature dimensions. So we have the expected feature from the search queue, we have the currently attended feature at the attended location, and if we have a peak in all 3 of these fields, I think that I skipped one. Working, okay, and the expected feature. Okay, and the mismatch detection. So the mismatch detection, my PC skipped the image. So the attended feature has an excitatory input to this mismatch detection field, and the expected feature has an inhibitory input, meaning that in this field only a peak will form when they are different, meaning signaling a mismatch. So if you have a peak in the attended feature, a peak in the mismatch detection, and a peak in the expected feature, the no match response will get activated and inhibit the match response, so it will not get activated. In the absence of a peak in the mismatch detection field, there's no inhibitory input to the match response, and so the match response will get activated. Okay, a single mismatch along all feature dimensions is enough to activate the condition of dissatisfaction, meaning that if one feature is off, it will always signal that there's no match between the attended location and the expected features. In contrast, the condition of satisfaction node will only get activated if all attended features match the search queue. Okay, together with the intention node, these 2 nodes are used to autonomously generate sequences of neural processing steps. Okay, task 1 is the visual exploration. This is the default behavior of the model. And In this mode, salient locations in the visual array are sequentially selected, brought into attentional foreground, and the features are then committed to working memory. This is a subnetwork responsible for the exploration and memory formation. It becomes active when the explore task node boosts the scene space selection field and the memory space feature selection fields, enabling them to generate peaks. As we already know, the scene space selection field forms a peak at a single location that's favored by its inputs. And then this attended location provides cylinder-shaped input to the set of three-dimensional scene space of feature selection fields that has the same structure as the scene space of feature maps described in the previously in the feed-forward path. So we see here this cylinder input, and we also have some sub-threshold input from the scene space of feature maps, meaning that peaks emerge on not working anything here. Peaks form where inputs from the scene space of feature maps overlaps with these spatially localized cylinders representing the features at the values at the attended object location. This information can then be extracted by integrating across the space so that we get only the feature information, and this can then serve as a slice input to the corresponding memory space feature maps, which is on the regime of sustained activation so that it can work as scene working memory. It also receives a cylinder input from the currently attended location, and only at the positions in space where the slice input and the cylinder input overlaps, peaks can form and be added to the scene working memory. Here also the number of peaks is limited by the, like in the previously in the spatial working memory. This is the same reason, because we need to have a capacity limit in working memory. And these fields serve as input to three analogous set of three space feature selection fields that also receive input as a sub-threshold input, and they also receive the cylinder input from the currently attended location. So we can also read out from memory the features at the current location that we have stored in memory. Okay. The result is an isolated representation of the memory item at the attended location. And then the feature matching subnetwork can compare the currently attended and the currently object in memory, and when both are equal, so the condition of satisfaction node of the feature matching subnetwork is activated, we know that the currently attended object was stored successfully in working memory. And then this deactivates the task node, and then one step is concluded in the sequence, and by default, if there's no other task, then it will be being reactivated and initiate a new cycle of attentional selection and commitment to working memory. So the second task is retaining the feature queue. This is the subnetwork responsible for it. The task node is activated by the onset detector, as I mentioned before, and then it will enable this gating mechanism, allowing that the currently attended information is stored in this search queue memory that's one-dimensional, because you're only interested in the feature values and not in the location. And when the information is stored, the feature matching algorithm detects that the information was stored correctly. It will deactivate inhibit the retain node, and then information in the retain gate and will decay. But the information in the search queue, since it's in the regime of of self-sustained activation, it will keep the information for later use. Okay, the last task is to find the queued object. So the third task node increases the likelihood that attention will be, so the network increases the likelihood that attention will be focused on the location where all the features are present. This is primarily achieved through top-down guidance from two sources, so the visual scene itself, called the scene guidance, and from scene memory, called memory guidance. Each of these include three-dimensional space feature overlap fields that receive subthreshold input from the scene feature maps in this case, or from the memory maps in this case, and also slice input from the feature queues. So peaks will emerge at So the subprocessor peak will emerge at locations where there's a sufficient overlap between the inputs. Okay, these peaks are projected into two-dimensional space guidance fields, and these both bias the attention selection and the scene space selection field. Okay. I really think that I have to stop the for a moment. I will have to stop the recording on my side because it's really atrocious. Okay, sorry.
No problem. I'm recording also,
yeah.
So should be no problem.
But it's impossible to work this way. So yeah, now it works. Perfect. So, okay, these peaks are projected back into the dimensional spatial guidance fields. Importantly, this spatial guidance field has a dynamic resting level that depends on the number of queued features by inhibitory connections. This field is dynamically downregulated. So each of these fields that contain a peak dynamically decreases the resting level of this field. Okay. This is also responsible for the difference between feature and conjunctive search, because in the case of the single feature search, peaks arise only at locations where the feature matches the current target queue, and in the conjunctive search case, non-target items will also become active as long as they share one feature with the target. The influence of memory on attention selection described thus far was only purely excitatory. And this excitatory bias is responsible for the faster reaction time, so for the change in the y-intercept. That was also reported by other experiments. An additional inhibitory influence is this spatial working memory field that inhibits locations that have been committed to memory during the exploration phase. And this influence decreased the likelihood that attention revisits such locations, but since inhibited location may also include the target item, the strength is low enough that it will be overruled by excitatory inputs. Okay, and this inhibitory bias from the spatial memory field explains the increased efficiency, so the change in the slope come from this inhibition. In the preview condition, of course. Yeah. If all features at the attended location match, the feature matching algorithm will the conditional selection will get activated, and this will signal task completion. If instead one or more queued feature values are not present at an location, the condition of dissatisfaction node of the feature matching component becomes active and inhibits the search task node, and then this will destabilize the scene space selection field, but also release the inhibition of the search node and then a new cycle of attention selection will occur. Okay, here are the results of the model. As you can see, the this change in the slope, the model is able to explain it, and also the salience in the y-intercept. Of course, we have to note that the overall magnitude of the reaction times is lower because there is some base time that is responsible for movement preparation and processing that is not modeled by our model. So it's normal to have a overall lower reaction times. So it's only important to see if the difference between the conditions in the y-intercept and the slope. And yeah, so the model is able to qualitatively fit the data of the experiments, and I also explained how this affects and the difference in the conditions emerged from the underlying dynamics of the model. So as I promised, I would present an extension to the model that's understanding the interplay between bottom-up processing and top-down guidance in visual search. First of all, we will have to give a very extensive overview of the problem itself so that you can understand it. If you don't have the background, I will try to keep it as fast as possible. So the capacity of the brain to process sensory stimuli is very limited. So neural resources have to be focused according to current contingencies, and this cognitive process is called attention. And attention can be categorized in two distinct functions. First of all, bottom-up attention and top-down attention. Bottom-up attention is the guidance driven purely by external factors, so the salience of the stimuli depends directly on the inherited properties relative to the background, like local feature contrast, so red, green, sudden movements. And it's the phylogenetically older system. Top-down attention is the attentional guidance driven by external factors. Okay, like prior knowledge, current task or goal, and also the guidance of visual search if there is a task and like you're seeking for a known object in an unknown location in the current scene. This leads us to the binding problem. So different attributes, features of a stimulus are processed by different areas of the cortex. Yet they are experienced in consciousness as a unity, as one object. And artificial neural networks currently ignore this problem. This problem was analyzed first by van der Maasbroek in 1999, and he called this problem the superposition catastrophe, meaning that if you have a single image of an apple, you can say, okay, it's a green apple. If you have a single image of a yellow pear, you can say the network can classify it as a yellow pear. But if you have a combined image of an apple, a red apple and a yellow pear, you will get the information that something red, something green, an apple and a pear, but the network lost this bound information and is not able to say it is a red apple and a green pear. You could also think that there's maybe a red pear in the image. And that's also why binding is highly relevant for correct knowledge representation that has been underestimated in artificial neural networks. But the major problem is it's completely unknown how the brain correctly links up all these different features. This led to the famous question if visual attention select objects or locations. And the effects associated with location-based attention are large and found consistently across experiments, and this favors highly binding through attentional selection of location. And feature integration theory is the prevalent theory, and it's most influential model of human visual attention, despite not being very neural. Was developed in the 80s by Anne Treisman and Gary Gillette. And features are abstracted in a paritative states, and objects are then features are bound by sequentially attentional selection. That's the attentional bottleneck that Professor Schöner talked earlier in the summer school. The opposing theory, meaning that object-based attention effects are small and less consistently, but they exist, and this is seen as evidence for binding without attention. Duncan and Humphreys and their similarity theory of attention is the as an alternative theory to feature integration theory. Objects are grouped by similarity, and the similarity between target and distracted is an important factor for reaction times. And the capacity limit of the visual working memory is the origin of the attentional bottleneck. And the problem was that some findings that cannot be explained by fit can be explained by the similarity theory. Guided search is probably the most prevalent model of visual search. It was invented by Jeremy Wolff in the 90s. It's in the spirit of feature integration theory, postulating binding through attention. And it was also able to explain the findings that feature integration theory failed to explain. So since both similarity theory and guided search delivered a plausible theory, the question if features are bound with or without attention remained open. Until 1998, when found provided evidence that a third feature that was correlated but irrelevant could improve the efficiency of conjunctive visual search. And since this was not consistent with the guided search model, but consistent with similarity theory, he proposed that the pre-attentive binding, how we called it, should be the correct solution to this question. Proul in 2007 expanded on this consideration and found that a salient task-irrelevant singleton also influenced search efficiency, but he found that both models, so guided search and similarity theory, wasn't able to explain his findings, and so he proposed that both models understated the role of bottom-up saliency, and he concluded that understanding the role of top-down and bottom-up guidance is crucial for models of visual search. Nordfang and Wolfe revisited in 2014 this triple conjunction search, and they found evidence that both grouping, so the number of different distractor groups in a search display, and feature sharing, the number of features shared between a distractor and a target, had a substantial effect on search efficiency. It may be not quite obvious, but the findings by Found and Proul, even they're not the same as as here in the triple conjunction case, but they are all interwoven. So there's the explanation for this for these findings will play a big role to understand the findings in Found and Proul. But they conclude that the findings could be explained by pre-attentive binding. We have to recall Wolff itself doesn't believe in pre-attentive binding, since its model is of course not a pre-attentive binding model, but he concluded that from his own findings he wasn't able to. He ran a lot of experiments. It was the most exhaustive experiment in this area, I think, and he couldn't find an explanation that rule out pre-attentive binding. But he also said that a very efficient top-down guidance based on a nonlinear sharing effect and or a nonlinear grouping effect in the bottom-up path could also account for observations without the need to resorting to this pre-attentive binding. But he never modeled it because he expected to be not trivial to model, so their verification remained open until today. So until today, there's no model of visual attention and or search able to explain these intriguing findings. Okay. So the question remained open until today. So this is a model we submitted to Coxside this year, and to ease the understanding, it's the same model I presented earlier. I removed everything that was related to subnetwork related to memory, scene memory, transient detection, because this is clearly a case where memory doesn't play no role because there's no preview. So I reduced the model to make it more accessible, but it's still the same model. And green outlines the subnetwork that were changed with respect to the previous model, and the changes were very minimal, as you will see, but highly crucial. Okay, and the feed-forward feature map, the small change was we replaced size by shape using a template matching. The non-neural algorithm was a very rough approximation of early shape detection in the human vision. And the most important change was we introduced projection kernel. So we had, as I mentioned earlier, we have this spatial readout. So there's projection from a 3-dimension to 2-dimension. So where activation is summed over, so integrated over the feature dimension. And previously it was only a linear transformation. But now we have a projection kernel, and the projection kernel is a center surround filter that has an excitatory kernel and an inhibitory center surround band, and they are used in many models like the E.T. und Koch, the famous E.T. und Koch bottom-up salience model. So and they are all very neurally plausible since they are a model of receptive fields. And this is how we change the bottom-up path, because this is very important and crucial, since we need to model how activation along one feature dimension interacts locally. So this is a meaning that there's a local self-excitation in the feature dimension and a local inhibition between features that are near to each other. It's important that it's not an local inhibitory that takes the object into consideration, since everything here is happening in these pre-attentive pathways, so meaning that these are different parts in the cortex, so there can only information that are in the same region can have an inhibitory influence to each other. So it's only purely in the feature domain that this inhibition occurs and this excitation. So if you take an example, this is the image provided, this is the input to this field. As you can see here, like for example, this green one here is highly salient and these blue ones are way less salient. This comes from this center surround projection kernel, and this is then the output of the field. And since we have already known that we have this non-singularity, so we have this sigmoid function in the field equation, the required non-linearity from Wolff's theory is already fulfilled by simply by using a dynamic neural field. That's very appealing for us, meaning we have an input that is linear and we get a non-linear output from the field. And this is also the Gaussian low-pass filtered version of it. That's a little bit easier to read. And we see that now the difference in between is less prominent. So we get this nonlinearity nicely from the field equation. And this is responsible for the grouping effect. And now the change in the top-down guidance is very small change, but also important. So previously we had this dynamic resting level and a very hard sigmoid, meaning that only information that was super threshold was really passed through this top-down path. The major change now was that we have a very soft sigmoid that's neurally way more plausible, but in the previous experiment we didn't need the information. So now also the subthreshold activation is still transmitted through this top-down path. And here we actually see an example image, and then we see that here in the input to this field, there's a linear activation pattern, meaning that the target here, this one has the activation of 3, the object sharing 2 features had an activation of 2, and object sharing 1 featured object an activation of 1. No? This is this linear activation map that is currently used in most of the state-of-the-art models, and maybe they have some kind of dimension weighting, but crucially was this nonlinearity, which also comes for free from our equation. So the output of the field is already a nonlinear version, but crucially, very important to fit the data is to find the correct value for this dynamic resting level, because of course the brain could use this information probably, and you would find the target instantaneously. But we know from experimental data that this is not the case, and you could also think about it why it's not the case. No? So in reality, when in conjunctive search, where the target is the only one that shares 2 features or 3 features in the triple conjunction with the queue, and this information is available, you could argue why not find it directly? Why does the object that share 2 features in the triple conjunction or 1 feature in the single conjunction search has a high impact that it can be that pre-attentively the system is not able to differentiate between the target and these destructors, despite it being different in 1 feature dimension. No? But if you think about it, that these features that are used are these pre-attentive features, they are roughly probably not highly accurate, and they should be very easy to get disrupted by lightning, by contrast, by local contrast of very near objects to each other. So from an evolution point of view, it really makes sense to say, okay, if I have 1 degree of freedom, so if I'm not seeking for the exact match, but an object that is able in 1 feature dimension, it may be off from my stored template in memory, then in a naturalistic scene, the probability that there are a lot of objects near to each other that only differ in 1 feature dimension, in reality, if you think introspectively about it, it's highly improbable. So if you forget these laboratory cases in naturalistic scenes, this seems to be a very realistic strategy to find objects even when due to lightning or other environmental influences, allowing that the feature dimension one feature dimension can be off, you will probably find faster your objects than if you have to really match perfectly, because if the system that evolved would be to perfect match, you probably wouldn't be able to find your objects in the moment where the lightning is dim or something, because the color would be completely different, and then you would get stuck. Okay, I don't find the perfect match, and then you would have to do an exhaustive search, and this is way more costly than saying, okay, I allow 1 dimension to be off, and then if the visual search becomes very efficient, that's probably the reason why human visual search is quite efficient, incredibly efficient oftenly, and it's also very efficient in this triple conjunction search, and this high efficiency in this triple conjunction search has created this puzzle. And the solution in this puzzle is really this, I call it, since I invented it, the n-1 rule, so this 1 degree of freedom, and that's something that emerged naturally from how our fields work. So we have this 1 field for each dimension, and then we have this field that receives the projected input. So the summed activation doesn't have this feature information, so it doesn't know if the activation is 2, it doesn't know which one of the feature dimension is off. So this is the one great strength against algorithm. Okay, I see there's a question in the chat. Okay. Against these algorithmic cases where people try to find some kind of algorithms that weights the dimension, we are agnostic to dimension. We all know at least 2 feature dimensions are equal to the target. We don't really care which one is off. And to enable this effect, we have this dynamic resting level, and this is responsible for the sharing effect. And here is a very simplified one-dimensional, non-realistic one-dimensional case where we can see how this works, because in 2 dimensions it's not so easy to see. So here we have one object that share one, and the distractor sharing 2 features and the target. And we see that this is the input activation, the blue one. The input activation linearly encodes the number of features. No? But if you take a look at the sigmoid activation, you will see that both the case where the target and the distractors that share n-1 features have the same nonlinear output in the field, so they have the same activation, sigmoidal activation, and the object that has shares one feature has it's not a big difference, but the small difference are amplified, are enough, since they in macroscopic point of view it's a real big difference, and this small difference here is also important because sometimes this object will get selected, and I will explain in a moment why. So, but importantly is that preattentively there's no difference in this guidance field, so in the output of the guidance field, between the target and the distractors. And this all you have to take into consideration that this dynamic down regulation is very important from DFT point of view, because if you didn't hit this dynamic raising level with increasing number of features, your activation would saturate, and then you would have no guidance effect. So now we will explain why it's also important that objects that share less than n-1 features has an impact, but it has to be a very small impact. So if you have a sample image, you see here the combined bottom-up output and the top-down output. So the 2 nonlinear maps we have, the guidance maps, are combined as an input to the scene space selection field. And here you can see that there are objects with one feature that are more salient than others because they have a higher bottom-up saliency. So this bottom-up saliency doesn't help to find the target, but is a source of noise, because if something is in the bottom-up path very salient, it will overcome this guidance. So even if the guidance said, okay, this is probably not an object that is interesting to look at because it has a high bottom-up saliency, it will still have compete for selection, and there will be cases where these objects will be selected. And this is also in the experimental data from Nordfang and Wolfe. So we have this efficient top-down guidance that is efficient in the sense of allowing in naturalistic scenes to find objects with a degree of freedom. But in this constructed laboratory cases, it has this distinct signature that it will lead to an inefficient search. And the difference in the bottom-up path are noise, since bottom-up path will not help, but this noise can create situations where it favors the target, meaning that if the target has a higher salience in the bottom-up path, but it's easy to understand that in how more if you have few groups of distractors and change the number, it will also change the probability that that the target will become more salient, but also non-targets will become more salient. So there's a trade-off of both sides. But this noise in the bottom-up path can create puzzling situations, and that's why for many years in this community they couldn't find the solution for this. Okay, so we will come to results, and then I'm done. And these are the 7 conditions they used in the experiments. So the number before the D is the number of groups and of the structure groups. so we had 3 distractor groups, 12 distractor groups, and 26 distractor groups. And in the parentheses we have the number of objects that share distractors that shares features with the target. So here we have all the distractors share 0 features, so a single feature search. Here all distractors share 1 feature. Here also, difference is the number of distractor groups. 0, 1, 2, we have 1/3 has 0, 1/3 has 1, and 1/3 has 2 features shared with the target. The 26D is a special case where all distractors are used, so but they're also roughly in the 0, 1, 2 distribution, and so on. And we see that this last case is where all objects share 2 features, is the classical conjunctive search. So the worst case is the case where preattentively there's no guidance. So here the top-down guidance will fail, and the probability of selecting object will only come from bottom-up noise. So if there wasn't bottom-up noise, all objects would have the same probability to be selected. The bottom-up noise will make that some are more visible, more have higher salience than other, but over tries it should be evened out. And if you look at the results, since I mentioned over tries it will be evened out, it's very important to note that since this bottom-up, we see that there's many different kinds of bottom-up groups. So this noise effect is very strong. So we have high variance in the bottom-up path. So if you use only few trials, and this was the case here, only had 50 trials for each condition and set size and so on, then this impact is stronger. And as you can see that they repeated it over many experiments, that the slopes for example here this condition was repeated, or this condition here was repeated 4 times, and you will see 4 different slopes. This comes from the high variance in the bottom-up path. So how did we compare the models to this? We created ranges that were not reported in the experiment, but we can create ranges over experiments, and we can create the mean, and then we can compare to our model. We also had 6 runs and can compare the means of it. And we see that the previous model that I presented at the beginning doesn't notice the difference between the conditions where there are different groups and the conditions where we have 0 or 1 feature. So here it was all single feature, and here all these cases were equal, and of course the conjunctive case it represented well. And that's the problem, because all models of visual search that currently exist, as I'm aware of, have this problem that they are not able to explain this difference. The changes we now made to the model, we can see that there's a very good approximation, and we can see of course they're not perfect, all slopes are not perfectly, but the difference between the conditions are all there. So we have this nice line up from the most efficient to the less efficient, and this is a very high quality fit, so meaning that the model really explains the underlying processes and delivers an answer to this long unanswered question. So a model that works in the spirit of feature integration theory, so that has attentional binding through space, so binding through attention, is able to explain this data that the similarity theory and others that don't use binding through space aren't able, and previous model that used binding through space, binding through attention also wasn't able, but it's to show that it is able to explain it. So it is a strong evidence, can be seen as strong evidence for binding through space being really the solution to the problem. Okay, the conclusion I will skip.